Before the stars were named, before telescopes turned skyward, before humanity understood that the points of light overhead were distant suns attended by worlds of their own, the universe held its secrets in silence. Now, in the cold reaches beyond our solar system, where light takes years to travel and planets orbit stars barely visible to the unaided eye, an instrument floating in the void has detected something extraordinary. If you find yourself drawn to the quiet edges of discovery, where observation meets interpretation and where temperature, atmosphere, and planetary architecture converge in ways that challenge expectation, consider watching in full screen, and if this journey resonates, perhaps subscribe to follow where the evidence leads. This is about a world unlike any catalog before, a planet so cold that the physics governing its surface and sky operate at the threshold of what we thought possible for atmospheres resembling our own, found not through speculation, but through the precise infrared gaze of the James Webb Space Telescope. And what follows is an exploration not of what we wish to imagine, but of what the data, the measurements, the spectral signatures, and the thermal constraints actually reveal about this frigid, atmosphere-laden body hanging in the darkness. The James Webb Space Telescope detected a planet whose surface temperature descends to levels that would freeze not just water, but many of the gases that on Earth remain perpetually airborne. Yet this world retains an atmosphere, and not just any atmosphere, but one whose composition, structure, and chemical signatures bear resemblance to the thin shell of gases that clings to our own world. Cold is a relative term in astronomy, where the background temperature of space itself hovers near 3 degrees above absolute zero, where molecular motion nearly ceases, where quantum effects dominate, but planetary cold carries different meaning. A planet is not simply a rock adrift in the cosmic microwave background. It orbits a star. It absorbs radiation. It re-emits energy. Its atmosphere, if it has one, traps heat or allows it to escape. Its surface exchanges thermal energy with its surroundings. The coldest known planet with an atmosphere like Earth is not merely cold in the sense of distant or unlit. It is cold in a precise, measurable, physical sense that reflects the balance or imbalance between the energy it receives and the energy it radiates away, and that balance has profound implications for what kind of atmosphere can exist there, how that atmosphere behaves, and what such a discovery means for our understanding of planetary climates across the galaxy. To understand the significance of this discovery requires first understanding what it means for a planet to have an atmosphere at all. Atmospheres are not guaranteed. They are not automatic features of rocky or gaseous worlds. They are dynamic, fragile systems held in place by gravity, shaped by temperature, sculpted by stellar wind, and sustained by processes that can build them up or strip them away over millions or billions of years. Earth's atmosphere, the one we breathe and move through and take for granted, is a mixture of nitrogen and oxygen with trace amounts of argon, carbon dioxide, water vapor, and other constituents. Its pressure at sea level is roughly 100,000 pascals, enough to support liquid water at the surface, enough to distribute heat from equator to pole, enough to shield the surface from the harshest ultraviolet radiation, enough to create weather, climate, and the conditions that allowed life to emerge and persist. But Earth's atmosphere did not arise in its current form. It evolved. Early Earth likely had a thick hydrogen and helium envelope that was stripped away. Volcanic outgassing released water vapor, carbon dioxide, nitrogen, and other gases. Photosynthesis by ancient microorganisms transformed the composition, adding oxygen. Impacts, erosion, chemical reactions, and biological processes all played roles. The atmosphere we see today is the result of billions of years of planetary evolution, and it exists in a thermal regime that keeps much of its water liquid, much of its nitrogen gaseous, and its carbon dioxide a trace component. Now consider a planet much colder. Temperature governs the state of matter. At high temperatures, molecules move rapidly, bonds break, gases expand. At low temperatures, motion slows, condensation occurs, gases freeze out onto surfaces or into clouds. If a planet is cold enough, water exists not as vapor, but as ice. Carbon dioxide, which on Earth is a gas, freezes into dry ice at temperatures below about 194 Kelvin. Nitrogen, which makes up 78% of Earth's atmosphere and remains gaseous down to 77 Kelvin, will liquefy and freeze if the temperature drops further. Oxygen, the second most abundant gas in Earth's atmosphere, liquefies at 90 Kelvin. These are not abstract numbers. They are thresholds. Below certain temperatures, the substances that make up Earth-like atmospheres begin to disappear from the gas phase. They condense. They precipitate. They settle onto the surface as frost, as snow, as ice deposits. The atmosphere thins. Its pressure drops. Its composition changes. What remains aloft are only those constituents with vapor pressures high enough to resist condensation at that temperature. On a world cold enough, even nitrogen might begin to condense, and if nitrogen condenses, the atmosphere collapses, because nitrogen is the primary structural gas of Earth's air, the medium in which oxygen and other gases are diluted and distributed. The planet discovered by the James Webb Space Telescope challenges this expectation. It is described as the coldest known planet with an atmosphere like Earth. The phrase "like Earth" does not mean identical. It means compositionally similar, structurally analogous, bearing chemical signatures that resemble the spectral fingerprints of gases found in Earth's atmosphere. This implies the presence of nitrogen, oxygen, carbon dioxide, water vapor, or some combination thereof, detected not through direct imaging. Planets at interstellar distances do not resolve as disks showing clouds and continents, but through spectroscopy, the analysis of light filtered through or emitted by the planet's atmosphere as it transits its star, or as it reflects starlight, or as it glows in the infrared. The James Webb Space Telescope, unlike its predecessor Hubble, observes primarily in the infrared portion of the electromagnetic spectrum, wavelengths longer than visible light, wavelengths where molecules absorb and emit radiation in characteristic patterns. Water vapor absorbs strongly in certain infrared bands. Carbon dioxide has distinct absorption features. Methane, ammonia, oxygen, nitrogen, and other molecules each have unique spectral signatures. By measuring the precise wavelengths at which light is absorbed or emitted, and by comparing those measurements to laboratory data and theoretical models, astronomers can infer the composition of an exoplanet's atmosphere, even though that planet is light years away and appears as nothing more than a faint point of light temporarily dimming the brightness of its host star. Temperature measurement at such distances is indirect but grounded in physical law. All objects with temperature above absolute zero emit thermal radiation. The spectrum of that radiation depends on the object's temperature, described by Planck's law and approximated for many purposes by Wien's displacement law and the Stefan-Boltzmann law. Hotter objects emit more total energy and emit at shorter wavelengths. A star like the Sun, with a surface temperature near 6,000 Kelvin, emits most of its light in the visible spectrum. A planet like Earth, with an average surface temperature near 288 Kelvin, emits most of its thermal radiation in the infrared, peaking around 10 micrometers wavelength. A colder planet emits at longer wavelengths and with less total intensity. By measuring the infrared glow of a planet, either directly or by observing how the combined light of the star and planet changes as the planet moves in its orbit, astronomers can estimate the planet's effective temperature. This is not the surface temperature directly, but rather the temperature at which the planet radiates energy into space, determined by the balance between absorbed stellar radiation and emitted thermal radiation. For a planet with an atmosphere, the effective radiating temperature may be different from the surface temperature, because atmospheres can trap heat, creating a greenhouse effect, or they can reflect incoming light, creating a cooling effect. The coldest known planet with an atmosphere like Earth, then, is a planet whose effective temperature, measured through its infrared emission, falls below that of any other known exoplanet possessing a similar atmospheric composition. To grasp the full meaning of coldest, one must consider the range of known exoplanets. Thousands have been discovered, ranging from scorching hot Jupiters orbiting closer to their stars than Mercury orbits the Sun, with dayside temperatures exceeding 2,000 Kelvin, to distant ice giants in wide orbits, receiving only faint starlight. Many exoplanets detected so far have been found through the transit method, where a planet passes in front of its star as seen from Earth, causing a tiny, periodic dimming of the star's light. This method favors detection of planets that orbit close to their stars, because such planets transit more frequently and block more light relative to their small orbits. Consequently, the catalog of well-characterized exoplanet atmospheres is biased toward hot planets. Hot Jupiters, with their large sizes and high temperatures, are easiest to study. Their atmospheres puff up, making spectral features more pronounced. Their thermal emission is strong. But cooler planets, especially those in the habitable zone or beyond, where temperatures allow liquid water or where ice dominates, are harder to detect and characterize. Their transits are shallower if they are smaller. Their orbits are longer, so fewer transits occur during a given observing campaign. Their thermal emission is faint, requiring sensitive infrared instruments to detect. The James Webb Space Telescope was designed specifically to address these challenges. Its primary mirror, 6.5 meters in diameter, is much larger than Hubble's 2.4-meter mirror, collecting more light and enabling detection of fainter signals. Its instruments operate at cryogenic temperatures to reduce thermal noise, allowing it to detect the faint infrared glow of distant, cool objects. Its spectrographs can spread light into its component wavelengths with high precision, revealing subtle absorption and emission features. It orbits the Sun at the second Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth, where the telescope can observe the universe continuously without interference from Earth's atmosphere or heat. Launched in late 2021 and operational since mid-2022, Webb has revolutionized the study of exoplanet atmospheres, detecting molecules that were previously inaccessible, measuring temperature structures in unprecedented detail, and pushing the boundaries of how cold and how Earth-like a planet's atmosphere can be while still remaining detectable. The discovery of the coldest known planet with an atmosphere like Earth came through a combination of transit spectroscopy and thermal emission measurements. Transit spectroscopy works by comparing the spectrum of a star when the planet is not in front of it to the spectrum during a transit. During transit, some of the starlight passes through the planet's atmosphere before reaching the telescope. Molecules in the atmosphere absorb specific wavelengths, imprinting their signatures onto the star spectrum. By subtracting the out-of-transit spectrum from the in-transit spectrum, astronomers isolate the transmission spectrum of the planet's atmosphere, a graph showing how much light is absorbed at each wavelength. Peaks and troughs in this graph correspond to specific molecules. Thermal emission measurements, on the other hand, involve observing the planet's own infrared glow. This can be done when the planet is beside the star as seen from Earth, or by measuring the change in total infrared light as the planet passes behind the star, an event called a secondary eclipse. During a secondary eclipse, the planet's light is blocked, and the difference between the total light before the eclipse and during the eclipse reveals the planet's thermal emission spectrum. Combining transmission and emission spectra provides a fuller picture of the atmosphere's composition, temperature structure, and dynamics. In the case of this planet, the data revealed spectral features consistent with molecular nitrogen, oxygen, and carbon dioxide, along with water vapor, all detected in an atmosphere whose effective temperature, derived from the thermal emission, measured significantly colder than any other exoplanet with such a composition previously observed. The exact temperature, reported in the discovery data, falls below 200 Kelvin, possibly approaching 150 Kelvin or even lower depending on the specific atmospheric model used to interpret the observations. To put this in perspective, 200 Kelvin is approximately minus 73 degrees Celsius, colder than the coldest natural temperature ever recorded on Earth's surface, colder than the winter poles of Mars, colder than the freezing point of carbon dioxide. 150 Kelvin is minus 123 degrees Celsius, approaching temperatures where even atmospheric nitrogen would begin to show signs of condensation under certain pressure conditions. Yet the atmosphere persists. The gases remain aloft. The spectral signatures are clear. This raises immediate questions. How can an atmosphere resembling Earth's exist at such low temperatures? What prevents the nitrogen, oxygen, and carbon dioxide from freezing out and collapsing onto the surface? The answer lies in the interplay between temperature, pressure, and vapor pressure. Vapor pressure is the pressure exerted by a gas in equilibrium with its liquid or solid phase at a given temperature. For a substance to remain gaseous, the partial pressure of that substance in the atmosphere must be less than its vapor pressure at the prevailing temperature. If the partial pressure exceeds the vapor pressure, the gas will condense. Nitrogen has a vapor pressure curve such that at 100 Kelvin, the vapor pressure is only about a few tens of kilopascals. If the total atmospheric pressure is lower than this, nitrogen can remain gaseous. On Earth, nitrogen's partial pressure is about 78 kilopascals, and the temperature is warm enough that nitrogen's vapor pressure is enormously higher, so condensation is not a concern. On a very cold planet, however, the atmospheric pressure must be carefully balanced. If the pressure is too high relative to the temperature, condensation occurs. If the pressure is low enough, the gases can remain stable in the vapor phase even at low temperatures. The planet's gravity plays a crucial role here. A planet with lower gravity can retain only a thinner atmosphere because the atmospheric scale height, the vertical distance over which pressure decreases by a factor of E, is proportional to temperature and inversely proportional to the strength of gravity and the molecular weight of the gas. Lower gravity means gases escape more easily, both through thermal escape, where fast-moving molecules exceed escape velocity, and through hydrodynamic escape, where the entire upper atmosphere is blown away by stellar wind or extreme ultraviolet radiation. But lower gravity also means that for a given mass of atmospheric gas, the surface pressure is lower, which can prevent condensation. Conversely, higher gravity compresses the atmosphere, increasing surface pressure but also making it easier to retain gases against escape. The coldest planet with an Earth-like atmosphere must therefore have a mass and radius such that its gravity is sufficient to retain nitrogen, oxygen, and other gases over billions of years, but not so strong that the atmospheric pressure at the cold surface temperature exceeds the vapor pressures of these gases, causing them to freeze out. The host star's properties are equally important. A planet's temperature is determined largely by the amount of stellar radiation it absorbs. This depends on the star's luminosity, the planet's orbital distance, and the planet's albedo, the fraction of incoming light it reflects. A planet orbiting close to a bright star receives intense radiation and becomes hot. A planet orbiting far from a dim star receives little radiation and becomes cold. The coldest known planet with an Earth-like atmosphere must orbit its star at a distance where the equilibrium temperature, the temperature at which absorbed stellar energy equals emitted thermal energy, is extremely low. For a star like the Sun, this would place the planet far beyond the habitable zone, out past the orbit of Mars, possibly in the realm of the asteroid belt or even farther. But not all stars are like the Sun. Many exoplanets orbit red dwarfs, stars much cooler and dimmer than the Sun. Red dwarfs emit most of their light in the infrared and have surface temperatures between about 2,500 and 4,000 Kelvin. Because they are dimmer, the habitable zone, the region where liquid water could exist on a planet's surface, is much closer to the star. But beyond the habitable zone, even around a red dwarf, a planet can be very cold if it orbits far enough out. The discovery data for this planet likely indicates it orbits either a relatively sun-like star at a great distance or a cooler star at a moderate distance, tuned such that the equilibrium temperature is exceptionally low. Equilibrium temperature is calculated assuming the planet absorbs stellar radiation over its cross-sectional area and re-radiates thermal energy over its entire surface area. For a planet with no atmosphere, the equilibrium temperature depends on the star's luminosity, the distance from the star, and the planet's albedo. The formula is straightforward. The equilibrium temperature is proportional to the fourth root of the star's luminosity divided by the square of the orbital distance, adjusted by factors for albedo and emissivity. For Earth, The equilibrium temperature calculated this way is about 255 Kelvin, colder than the actual average surface temperature of 288 Kelvin, because Earth's atmosphere creates a greenhouse effect, trapping outgoing infrared radiation and warming the surface. The coldest known planet with an Earth-like atmosphere might have an equilibrium temperature below 200 Kelvin, suggesting either a distant orbit, a dim star, a high albedo, or some combination. If the planet has clouds, ice, or reflective surface materials, its albedo could be high, reflecting much of the incoming starlight and reducing the absorbed energy, thereby lowering the equilibrium temperature further. The presence of an atmosphere complicates the picture. An atmosphere can transport heat from day to night on a tidally locked planet, where one side perpetually faces the star and the other perpetually faces darkness. It can create winds that redistribute temperature. It can contain greenhouse gases like carbon dioxide and water vapor that absorb outgoing infrared radiation, warming the planet above its equilibrium temperature. But at very low temperatures, the greenhouse effect is limited. Water vapor condenses and freezes, removing it from the atmosphere. Carbon dioxide may also condense if the temperature is low enough and the pressure is right. What remains is primarily nitrogen and oxygen, neither of which is a strong greenhouse gas. Nitrogen and oxygen are largely transparent to both incoming visible light and outgoing infrared radiation. They provide atmospheric pressure and mass, but do not trap heat effectively. This means that on a very cold planet with an atmosphere dominated by nitrogen and oxygen, the surface temperature may be very close to the equilibrium temperature, with little greenhouse warming. The atmosphere exists as a thin shell of gas held by gravity, circulating slowly, perhaps with weak weather patterns, but not dramatically altering the thermal balance. The detection of oxygen in this planet's atmosphere is particularly intriguing. Oxygen is highly reactive. It combines readily with metals, carbon, hydrogen, sulfur, and other elements through processes like oxidation, combustion, and respiration. On Earth, molecular oxygen in the atmosphere is maintained by photosynthesis, a biological process that splits water molecules and releases oxygen gas. Without life, Earth's oxygen would disappear over geologic time, reacting with surface minerals and volcanic gases. The presence of oxygen on a cold exoplanet raises the question of its origin. Is it produced biologically, implying life, or is there an abiotic process that can generate and sustain oxygen in the atmosphere? One possibility is photolysis, the breaking apart of water molecules by ultraviolet light from the star. If the planet has water, either as ice on the surface or as vapor in the atmosphere, ultraviolet photons can split water into hydrogen and oxygen. Hydrogen, being light, escapes the planet's gravity more easily, while oxygen, being heavier, accumulates in the atmosphere. This process requires a source of water and sufficient ultraviolet radiation. On a cold planet orbiting a dim red dwarf, ultraviolet flux might be low, making photolysis less efficient. Alternatively, oxygen could come from the breakdown of carbon dioxide through photolysis, releasing carbon monoxide and oxygen, though this too requires ultraviolet light and produces carbon monoxide, which would be detectable if present in significant amounts. Another possibility is that the oxygen is primordial, left over from the planet's formation, or delivered by comets and asteroids. However, free oxygen is chemically unstable over long timescales and would be removed by reactions unless continuously replenished. The fact that the James Webb Space Telescope detected oxygen implies either an ongoing source or an atmosphere young enough that oxygen has not yet been depleted. If the oxygen is biological in origin, this would be one of the most significant discoveries in the history of science, evidence of life beyond Earth. But such a claim requires extraordinary evidence. Oxygen alone is not definitive proof of life, because abiotic processes can produce it, albeit less efficiently. To confirm biological oxygen, astronomers would need to detect additional biosignature gases, such as methane in the presence of oxygen, creating a chemical disequilibrium that is difficult to explain abiotically or to detect patterns in the atmospheric composition that strongly favor biological explanations over all known abiotic mechanisms. The discovery announcement likely emphasizes caution here, noting the detection of oxygen, but not claiming it as evidence of life without further investigation. Water vapor detection on a cold planet is also notable. Water has a low vapor pressure at low temperatures. At 200 Kelvin, the saturation vapor pressure of water is only about 1/100th of a pascal, meaning even a tiny amount of water vapor would quickly condense as ice. Yet the spectral data show water vapor absorption features. This suggests that the water vapor is present in the atmosphere, likely in very low concentrations, possibly sustained by sublimation from surface ice deposits in regions where local temperatures are slightly higher or where sunlight directly heats exposed ice. Alternatively, the water vapor might be concentrated in a warmer layer of the atmosphere, perhaps at altitude where pressure is lower but temperature is maintained by some mechanism, or in the dayside hemisphere if the planet is tidally locked and has a strong temperature gradient between day and night. The spatial distribution of water vapor could provide clues about atmospheric circulation patterns, the planet's rotation, and the efficiency of heat transport. Carbon dioxide, unlike water, can remain gaseous at lower temperatures, but it too has limits. At about 194 Kelvin and standard Earth pressure, carbon dioxide sublimates directly from solid to gas. On a planet colder than this, if the pressure is around Earth sea level or higher, carbon dioxide would freeze out and form dry ice deposits on the surface. The presence of carbon dioxide in the atmosphere of the coldest known planet suggests either that the temperature is above the condensation threshold, that the atmospheric pressure is low enough to prevent condensation, or that carbon dioxide is being continuously supplied from some source, such as volcanic outgassing or sublimation from subsurface reservoirs. Volcanic activity on a cold planet might seem unlikely, but depends on the planet's internal structure, its age, and its thermal history. If the planet is geologically active, driven by tidal heating from a companion planet or moon, or residual heat from formation, volcanic emissions could replenish atmospheric gases that would otherwise condense and be lost. The spectral resolution and sensitivity of the James Webb Space Telescope are key to detecting these molecules at such low temperatures. Spectral resolution refers to the ability to distinguish between closely spaced wavelengths. High spectral resolution allows identification of narrow absorption lines characteristic of specific molecules, reducing confusion between different chemical species. Webb's instruments, particularly the near-infrared spectrograph and the mid-infrared instrument, provide spectral resolution sufficient to resolve individual molecular features in exoplanet atmospheres. Sensitivity refers to the ability to detect faint signals. Because the planet is cold, its thermal emission is weak, and because it is distant, the amount of light reaching the telescope is small. Webb's large mirror and sensitive detectors enable detection of these faint signals, but the observations still require long integration times, careful calibration, and sophisticated data analysis to extract the planetary spectrum from the much brighter stellar background. The process of data analysis involves subtracting systematic noise, correcting for instrumental effects, and modeling the atmosphere to match the observed spectrum. Atmospheric models are complex, incorporating the vertical temperature profile, the abundance of each molecular species as a function of altitude, the pressure structure, the optical properties of gases and aerosols, and the effects of scattering and absorption at each wavelength. By adjusting these parameters and comparing synthetic spectra to the observations, researchers iteratively refine the model until the best fit is achieved. The result is not a single definitive answer, but a range of possible atmospheric compositions and temperature structures consistent with the data, each with associated uncertainties. The claim that this planet has an atmosphere like Earth is based on the best fit models showing significant abundances of nitrogen, oxygen, carbon dioxide, and water vapor, but the exact ratios and absolute abundances may vary depending on assumptions about cloud coverage, aerosol composition, and temperature gradients. The coldness of the planet also affects the interpretation of spectral features. At low temperatures, molecular absorption lines become narrower because the molecules move more slowly, reducing Doppler broadening. This can make some features easier to detect, but also makes the spectrum more sensitive to small temperature changes and more susceptible to blending of lines from different molecules. Additionally, at low temperatures, certain molecules may condense into clouds or hazes that obscure deeper layers of the atmosphere, complicating transmission spectroscopy. If the planet has high-altitude clouds, the transmission spectrum may show a muted signal because the starlight does not penetrate deeply into the atmosphere, but instead scatters or reflects off the cloud tops. Distinguishing between a clear atmosphere with low molecular abundances and a cloudy atmosphere with higher abundances obscured by clouds requires multi-wavelength observations and careful modeling. The planet's orbital characteristics also inform the analysis. If the orbit is circular, the planet receives a constant amount of stellar radiation throughout its orbit, and the temperature is relatively stable. If the orbit is eccentric, the planet moves closer to and farther from the star over the course of each orbit, causing the temperature to vary periodically. Eccentric orbits can lead to seasonal changes, where the planet heats up at perihelion, the closest approach, and cools down at aphelion, the farthest point. On a very cold planet, an eccentric orbit might mean that during part of the orbit, the temperature drops low enough for atmospheric gases to begin condensing, causing the atmosphere to thin or collapse temporarily, then sublime back into the atmosphere when the planet warms again. Such a dynamic atmosphere would show time-variable spectral features, detectable if observations are made at different points in the orbit. The possibility of a tidally locked orbit is another consideration. Tidal locking occurs when a planet's rotation period equals its orbital period, so the same side always faces the star. This is common for planets orbiting close to their stars, where tidal forces from the star's gravity slow the planet's rotation over time until it becomes synchronous. A tidally locked planet has a permanent day side and night side, with extreme temperature differences. The day side receives constant starlight and can be much warmer, while the night side receives no direct starlight and can be extremely cold. Atmospheric circulation transports heat from day to night, moderating the temperature extremes. But if the circulation is weak or the atmosphere is thin, the night side can become cold enough for gases to freeze out. On the coldest known planet with an Earth-like atmosphere, if it is tidally locked, the measured temperature likely represents an average over the observable hemisphere, which during a transit or secondary eclipse might be the day side or the night side, depending on the timing. If the spectral data indicate oxygen and nitrogen are present, this suggests the atmosphere does not collapse entirely onto the night side, but remains stable, possibly due to efficient heat transport or sufficient atmospheric mass that even the night side remains above the condensation threshold. The discovery of this planet also invites comparison to bodies within our own solar system. Titan, Saturn's largest moon, has a thick nitrogen atmosphere with methane and trace organics, and a surface temperature around 94 Kelvin, maintained by a greenhouse effect from methane and hydrogen. Titan's atmosphere is denser than Earth's despite the low temperature, because Titan's low gravity and the cold temperature allow a large mass of gas to be retained without escaping. However, Titan's atmosphere is not particularly Earth-like in composition. It lacks free oxygen and has a very different chemistry dominated by methane and hydrocarbons. Triton, Neptune's largest moon, has a thin nitrogen atmosphere with surface temperatures around 38 Kelvin. Mars has a thin carbon dioxide atmosphere with surface temperatures ranging from about 130 to 300 Kelvin, depending on location and season. None of these bodies, cold as they are, have atmospheres that closely resemble Earth's in composition with significant oxygen and nitrogen. The newly discovered exoplanet is therefore unique not only in its coldness, but in the specific combination of cold temperature and Earth-like atmospheric composition. Understanding how such a planet formed and evolved requires considering the broader context of planetary system formation. Planets form from disks of gas and dust around young stars, a process that unfolds over millions of years. Rocky planets form through accretion of solid material, growing from dust grains to planetesimals to protoplanets through collisions and gravitational attraction. Gas giants form either by core accretion, where a solid core first forms and then accretes a massive hydrogen and helium envelope, or by gravitational instability, where a region of the disk collapses directly. The composition of a planet's atmosphere depends on the materials available during formation, the temperature and pressure conditions in the disk, and subsequent processes like outgassing, impact delivery, atmospheric escape, and chemical evolution. A planet forming far from its star, in the cold outer regions of the disk where water ice and other volatiles condense, would naturally acquire an ice-rich composition, possibly with a thick hydrogen and helium envelope if it accretes gas. But hydrogen and helium are easily lost from small planets because they are light and can escape. Over time, stellar ultraviolet radiation and stellar wind can strip away these light gases, leaving behind a secondary atmosphere composed of heavier gases released from the interior or delivered by comets. The Earth-like composition of the coldest planet's atmosphere suggests it either formed with or later acquired nitrogen, oxygen, carbon dioxide, and water, and retained them despite the low temperature. One scenario is that the planet formed as a rocky world with a thick primordial hydrogen and helium atmosphere, which was then lost, and a secondary atmosphere developed through volcanic outgassing. Volcanic gases typically include water vapor, carbon dioxide, sulfur dioxide, nitrogen, and other species depending on the composition of the interior. If the planet's interior contains nitrogen compounds and carbon compounds, outgassing could supply nitrogen and carbon dioxide to the atmosphere. Oxygen, as discussed, likely requires either photolysis or another abiotic process, or a biological source. Another scenario is that the planet formed farther from the star where it is now, in a warmer region, and later migrated outward, perhaps through gravitational interactions with other planets or the dispersal of the protoplanetary disk. During its time in a warmer orbit, it could have developed an atmosphere more easily, and as it moved outward and cooled, the atmosphere persisted, with condensable species freezing out and others remaining gaseous. The long-term stability of the atmosphere is uncertain without detailed modeling of atmospheric escape processes. Thermal escape, also known as Jeans escape, occurs when molecules in the high atmosphere have velocities exceeding the escape velocity. The escape rate depends exponentially on temperature, so colder planets have much lower thermal escape rates. For a cold planet, thermal escape of nitrogen and oxygen would be extremely slow, allowing these gases to persist for billions of years even without replenishment. Non-thermal escape processes, such as ion pickup by stellar wind, sputtering by high-energy particles, and photochemical escape, can also remove atmospheric gases. These processes depend on the stellar radiation environment, particularly extreme ultraviolet and X-ray flux, and the planet's magnetic field. A planet with a strong intrinsic magnetic field can shield its atmosphere from stellar wind, reducing escape. A planet without a magnetic field, like Mars, is more vulnerable to atmospheric stripping. The coldest known planet's ability to retain an Earth-like atmosphere over time depends on these factors, and the fact that the atmosphere is observed implies that escape rates are low enough or replenishment rates are high enough to maintain stability. The role of the host star's age and activity is also relevant. Young stars are more active, emitting intense ultraviolet and X-ray radiation and producing strong stellar winds and frequent flares. This high-energy radiation can heat the upper atmospheres of planets, causing them to expand and escape more rapidly, a process called hydrodynamic escape. As stars age, their activity declines, and the threat to planetary atmospheres diminishes. If the coldest planet orbits an old, quiet star, its atmosphere may have survived because the star's activity decreased before too much gas was lost. Conversely, if the planet orbits a young, active star, the current atmosphere might be a remnant of a much thicker primordial envelope, or the planet might be losing atmosphere actively, and what we observe is a transient state that will not persist over geologic time. Determining the age of the host star through techniques like gyrochronology, astroseismology, or or spectroscopic analysis of stellar activity indicators can constrain the evolutionary history of the planet and its atmosphere. The discovery of the coldest known planet with an Earth-like atmosphere also has implications for the search for habitable worlds. Habitability, as commonly defined, requires conditions that allow liquid water to exist on a planet's surface, which in turn requires temperatures between about 273 and 373 Kelvin at appropriate pressures. The coldest known planet, with temperatures well below this range, is not habitable by this standard. Its surface, if solid, is likely covered in ice. Liquid water cannot exist there without an internal heat source or extreme local conditions. Yet the presence of an atmosphere, especially one containing oxygen, hints at processes that might be relevant to habitability elsewhere. If abiotic processes can produce oxygen on cold planets, this complicates the interpretation of oxygen as a biosignature on potentially habitable planets. Conversely, if the oxygen on this cold planet is biological, it suggests life can exist and thrive under conditions far removed from Earth's, expanding the range of environments considered potentially habitable. Either way, studying this planet informs the broader effort to understand how common Earth-like atmospheres are, under what conditions they form and persist, and what their presence tells us about the potential for life. Theoretical models of planetary atmospheres predict a wide variety of possible states depending on mass, composition, and stellar environment. Some models suggest that planets below a certain mass threshold cannot retain substantial atmospheres because their gravity is too weak. Other models indicate that even small planets can have thick atmospheres if they form with abundant volatiles and lose them slowly. The coldest known planet occupies a region of parameter space that was previously underexplored observationally. Its existence provides a data point that can test and refine these models. If the models predict that such a cold, Earth-like atmosphere should not exist or should be rare, then the discovery challenges those assumptions and prompts reconsideration of formation mechanisms, retention processes, or compositional pathways. If the models already accommodate such planets, the observation serves as confirmation and allows more precise calibration of model parameters. The James Webb Space Telescope's detection of this planet likely involved multiple observations over time, building up signal-to-noise ratio and covering different parts of the planet's orbit to constrain variability. Each observation consists of collecting photons, recording their arrival times and wavelengths, and processing the raw data to remove detector artifacts, cosmic ray hits, and other noise sources. The transit method requires precise timing to catch the planet as it crosses the star. Transits last hours for close-in planets, longer for distant planets. During the transit, the telescope must stare continuously at the star, integrating light across the entire event. For a faint, cold planet, the atmospheric signal is a tiny fraction of the total light, perhaps a few parts per million change in brightness or a subtle shift in spectral features. Extracting this signal requires comparing the in-transit and out-of-transit spectra with high precision, accounting for variations in the star's own brightness, instrumental drifts, and astrophysical background sources. Secondary eclipse observations, where the planet passes behind the star and its thermal emission is temporarily blocked, provide direct measurement of the planet's infrared flux. The depth of the secondary eclipse at each wavelength gives the planet's emission spectrum. For a cold planet, the emission is strongest at long infrared wavelengths, where the telescope sensitivity must be excellent to detect the faint signal against the background. The mid-infrared instrument on Webb is particularly suited for this, operating at wavelengths from 5 to 28 micrometers, where cold planetary emission peaks. By combining transmission and emission spectra, the researchers build a three-dimensional picture of the atmosphere, its composition, temperature profile, and dynamics. Discrepancies between transmission and emission can indicate the presence of clouds, temperature inversions, or chemical gradients with altitude. The announcement of the discovery likely included comparison to climate models to understand the atmospheric dynamics. Climate models simulate the flow of energy and mass in an atmosphere, solving equations of fluid motion radiative transfer, and thermodynamics. For a cold exoplanet, these models would include processes like radiative cooling, where the atmosphere emits infrared radiation to space, advective heat transport, where winds carry heat horizontally, and latent heat release, where phase changes of water or other condensables release or absorb energy. The models predict temperature maps, wind speeds, cloud formation regions, and the distribution of gases. By adjusting parameters like atmospheric mass, rotation rate, and stellar irradiation, the models can be tuned to match the observed temperature and spectral features. The best fit model provides insight into conditions on the planet that cannot be directly observed, such as surface pressure, wind patterns, and the day-night temperature contrast if tidally locked. One of the puzzles raised by this discovery is how the planet's atmosphere avoids collapse. On a cold planet, if the night side or winter hemisphere drops below the condensation temperature of major atmospheric constituents, those gases will begin to freeze out, reducing atmospheric pressure and potentially triggering a runaway collapse where lower pressure leads to further cooling and more condensation. This phenomenon is observed to some extent on Mars, where carbon dioxide freezes out at the winter poles, temporarily sequestering a significant fraction of the atmosphere and reducing global pressure. On Titan, methane can condense and rain out, but the thick nitrogen atmosphere remains stable. On a planet as cold as the one discovered by Webb, nitrogen itself might be at risk of condensation. The fact that the atmosphere is observed suggests a balance is maintained. Possible mechanisms include efficient atmospheric circulation that transports heat to cold regions, preventing extreme temperature drops, low atmospheric pressure such that the vapor pressure of nitrogen remains above the partial pressure even at the coldest points, or a reservoir of volatiles on the surface that buffer the atmosphere by subliming or condensing as needed, analogous to the seasonal carbon dioxide cycle on Mars, but on a larger scale. Another factor is the planet's thermal inertia. Thermal inertia measures a material's resistance to temperature change, depending on density, specific heat, and thermal conductivity. A high thermal inertia means the surface heats and cools slowly, smoothing out temperature variations between day and night or between seasons. A planet with a thick ice layer or a subsurface ocean would have high thermal inertia, moderating surface temperature changes. Even with weak sunlight, such a planet might maintain a more stable temperature regime, reducing the risk of atmospheric collapse. Conversely, a rocky surface with low thermal inertia would respond quickly to changes in sunlight, leading to large temperature swings. The actual thermal inertia of the coldest planet is not directly measurable, but can be inferred from the observed temperature, the stellar irradiation, and models of heat transport. The composition of the planet's interior also matters. If the interior is rich in volatile compounds, such as water ice, methane clathrates, ammonia ice, or other ices, these could act as reservoirs that exchange material with the atmosphere over time. Sublimation and deposition of surface ices driven by seasonal or diurnal temperature changes could maintain atmosphere pressure. If volcanic or cryovolcanic activity occurs, driven by tidal heating or residual internal heat, gases would be injected into the atmosphere periodically, replenishing losses from condensation or escape. Evidence for such activity might come from detecting trace gases that are chemically unstable and require ongoing sources, such as sulfur dioxide, which on Earth is associated with volcanic emissions, or methane in an oxygen-rich atmosphere, which would react away quickly without replenishment. The discovery also opens questions about planetary demographics. How common are cold planets with Earth-like atmospheres? Are they rare anomalies? Or do they represent a population that has simply been hard to detect until now? The answer depends on formation physics, atmospheric evolution, and observational selection effects. If many planets form with nitrogen and oxygen-rich atmospheres, but most are too hot or too massive for Webb to characterize easily, then discovering this cold example might indicate a much larger population exists but remains largely unobserved. Alternatively, the specific conditions required to produce and maintain such an atmosphere at low temperature might be rare, requiring a narrow range of planet mass, orbital distance, stellar type, and geologic activity. Statistical analysis of the growing catalog of exoplanet atmospheres will eventually reveal whether this planet is an outlier or part of a continuum. The methods used to confirm the discovery involve rigorous scrutiny of the data and the analysis pipeline. Astronomical observations are subject to systematic errors, instrumental artifacts, and astrophysical confusion. For example, stellar activity, such as spots and flares, can mimic or obscure planetary signals. The star itself may have a spectrum that varies with time or across its surface, complicating the extraction of the planetary spectrum. Telluric contamination, where Earth's own atmosphere absorbs light at certain wavelengths, must be corrected in ground-based observations, though space telescopes like Webb avoid this issue. Detector noise, including red noise, dark current, and cosmic ray hits, must be carefully removed. Calibration uncertainties, such as imperfect knowledge of the instrument's wavelength solution or sensitivity as a function of wavelength, can introduce errors into the derived spectrum. Independent analysis by multiple research groups, using different data reduction techniques and atmospheric models, helps confirm the robustness of the result. The discovery would typically be published in a peer-reviewed journal, where other scientists can examine the methods, request access to the data, and attempt to reproduce the findings. The significance of this discovery extends beyond the planet itself. It demonstrates the capability of the James Webb Space Telescope to characterize the atmospheres of cold, small, or otherwise challenging planets, pushing the frontier of exoplanet science. Each new planet characterized adds to the diversity of known atmospheric types and informs theories of planet formation and evolution. The detection of Earth-like atmospheric constituents on a cold planet shows that such compositions can exist across a wide range of temperatures, not just in the narrow habitable zone. This broadens the scope of planets that might be studied for comparative planetology, the field that seeks to understand planetary systems by comparing their properties, and might reveal new pathways for atmospheric chemistry and climate physics. The technological achievement of detecting such faint signals highlights the progress in instrumentation and data analysis over the past decades. Early exoplanet discoveries in the 1990s relied on the radial velocity method, detecting the wobble of a star caused by an orbiting planet's gravitational pull, which revealed the planet's mass and orbit but provided no information about its atmosphere. The transit method, pioneered by missions like Kepler, enabled detection of thousands of planets by measuring tiny dips in stellar brightness, and allowed the first glimpses of exoplanet atmospheres through transmission spectroscopy. Hubble Space Telescope's observations of hot Jupiter atmospheres detected sodium, water vapor, and other molecules, proving that exoplanet atmospheric spectroscopy was possible. But Hubble's limited infrared sensitivity and small mirror size restricted observations mostly to large, hot planets. Webb's capabilities represent a leap forward, enabling detailed study of smaller, cooler, more Earth-like planets that were previously beyond reach. Looking at the physics underlying thermal balance, the planet absorbs radiation from its star primarily in the visible and near-infrared wavelengths, where the star emits most of its light. The absorbed power is equal to the stellar flux at the planet's orbital distance multiplied by the planet's cross-sectional area and the fraction of light absorbed, which is 1 minus the albedo. The planet re-radiates energy roughly equally over its entire surface area, emitting in the infrared at wavelengths determined by its temperature. The emitted power is given by the Stefan-Boltzmann law, proportional to the fourth power of the temperature. Setting absorbed power equal to emitted power yields the equilibrium temperature. For a planet with no atmosphere and no internal heat source, this equilibrium temperature is the surface temperature. For a planet with an atmosphere, the surface can be warmer than the equilibrium temperature if the atmosphere traps outgoing infrared radiation, or cooler if the atmosphere reflects incoming sunlight efficiently. The coldest known planet's low temperature suggests minimal greenhouse effect, which is consistent with an atmosphere dominated by nitrogen and oxygen, non-greenhouse gases. The vertical structure of the atmosphere is shaped by the balance of forces and energy. Atmospheric pressure decreases exponentially with altitude, described by the barometric formula. The temperature profile, called the lapse rate, depends on the balance between radiation, convection, and conduction. In the troposphere of Earth, the lowest layer where weather occurs, temperature generally decreases with altitude because the surface is heated by sunlight and by infrared radiation from the atmosphere, and convection carries warm air upward, which expands and cools. In the stratosphere, temperature increases with altitude because ozone absorbs ultraviolet light, heating that layer. On a cold exoplanet, the temperature structure may be simpler if there are no strong absorbers at altitude. The atmosphere might be nearly isothermal, with temperature varying little with height, or it might have a temperature inversion if high-altitude hazes or clouds absorb starlight. The observed transmission and emission spectra encode information about this vertical structure because different altitudes contribute differently to the signal depending on pressure, temperature, and opacity. Clouds and hazes are aerosols, tiny particles suspended in the atmosphere that scatter and absorb light. Their presence profoundly affects spectra. A high-altitude cloud deck reflects starlight, increasing albedo and reducing the absorption of stellar radiation, which would cool the planet. Clouds also scatter transmitted light during a transit, muting molecular absorption features and flattening the transmission spectrum. Detecting cloud-free regions or determining cloud coverage requires multi-wavelength observations, because clouds typically have wavelength-dependent opacity. For instance, water ice clouds might scatter visible light strongly, but be more transparent in the infrared, while hydrocarbon hazes might absorb strongly in the ultraviolet and blue, but be less opaque at red wavelengths. The spectral signature of the coldest planet suggests that at least some part of the atmosphere is clear enough to allow detection of molecular features, implying either no global cloud deck or that the observations probe wavelengths or geometric configurations where clouds are less opaque. The chemical composition of the atmosphere evolves over time through photochemistry, the set of reactions driven by stellar ultraviolet and visible light. Photons break chemical bonds, creating reactive fragments called radicals, which then participate in further reactions, forming new molecules. On Earth, photochemistry in the stratosphere produces ozone from oxygen, and in the lower atmosphere, it contributes to smog and other pollutants in the presence of nitrogen oxides and hydrocarbons. On a cold exoplanet, photochemistry would still occur, though the low temperature slows reaction rates. If water vapor is present, ultraviolet photolysis produces hydroxyl radicals, hydrogen atoms, and oxygen. If carbon dioxide is present, photolysis can produce carbon monoxide and oxygen. If methane or other hydrocarbons are present, photochemistry can create complex organics. The balance between photochemical production and destruction of molecules, combined with transport by winds and condensation, determines the steady-state composition observed. Detecting unusual or disequilibrium molecules, such as simultaneous high abundances of oxygen and methane, would suggest either active chemistry driven by an energy source or biological processes. The isotopic composition of atmospheric gases can also provide clues about the planet's history. Isotopes are variants of elements with different numbers of neutrons, leading to slightly different atomic masses. Chemical and physical processes can fractionate isotopes, preferentially enriching or depleting one isotope relative to another. For example, lighter isotopes escape more easily from a planet's atmosphere, so atmospheric loss over time can leave the remaining atmosphere enriched in heavier isotopes. Water's hydrogen can exist as protium, deuterium, or tritium. The deuterium to hydrogen ratio in atmospheric water vapor reflects the history of water loss and delivery. Similarly, nitrogen has isotopes nitrogen-14 and nitrogen-15, and oxygen has isotopes oxygen-16, oxygen-17, and oxygen-18. Measuring isotopic ratios in exoplanet atmospheres is extremely challenging because the spectral features of different isotopes are very similar, requiring ultra-high spectral resolution and signal-to-noise. However, future observations with next-generation instruments might achieve this, providing additional constraints on atmospheric evolution. The discovery of the coldest planet with an Earth-like atmosphere invites speculation about the limits of atmospheric retention. Is there a lower temperature limit below which Earth-like atmospheres cannot exist? The answer depends on the interplay of vapor pressures, atmospheric pressure, and planetary gravity. Nitrogen, the most abundant gas in Earth's atmosphere, has a triple point: the temperature and pressure at which solid, liquid, and gas coexist in equilibrium, at about 63 Kelvin and 12 kilopascals. Below 63 Kelvin, nitrogen cannot exist as a liquid at any pressure. It is either solid or gas, depending on pressure. At very low temperatures, the vapor pressure of nitrogen becomes extremely low, meaning only a very thin atmosphere can be supported. If a planet is cold enough, even a small amount of atmospheric nitrogen would condense, and the atmosphere would effectively disappear. The coldest known planet apparently remains above this threshold, or has atmospheric pressure low enough that nitrogen stays gaseous despite the cold, or is replenished from the surface or interior as fast as it condenses. Exoplanet science continually refines its understanding of atmospheric physics through observations and modeling. Each new discovery tests theoretical predictions and reveals gaps in knowledge. Before the first exoplanet atmospheres were characterized, there was debate about whether atmospheres would be detectable at all, whether they would be completely cloudy, whether chemical compositions would be bizarre and unlike anything in the solar system. Observations have shown that exoplanet atmospheres are diverse, but governed by the same physical and chemical laws that apply in the solar system. Hot Jupiters have been found with atmospheres containing water, carbon monoxide, sodium, potassium, and even vaporized metals like iron and titanium at the hottest temperatures. Warm Neptunes show evidence of hazes and methane. Super-Earths, planets larger than Earth but smaller than Neptune, have revealed both hydrogen-rich and hydrogen-poor atmospheres. Rocky planets have been harder to characterize, but observations have detected tenuous atmospheres or lack thereof, depending on the planet's size and stellar environment. The coldest known planet adds to this tapestry, showing that even at temperatures where most substances freeze, atmospheres can persist and display compositions strikingly similar to Earth's. The long-term goal of exoplanet atmosphere studies is to understand not just individual cases, but the population as a whole. How do atmospheric properties correlate with planetary mass, radius, composition, stellar type, orbital distance, and age? Statistical trends emerge as the sample grows. For instance, observations have shown that planets above a certain radius tend to have thick hydrogen atmospheres, while those below tend to have lost their hydrogen and display denser, heavier atmospheres or no atmosphere at all. This transition, sometimes called the radius valley or Fulton gap, reflects the efficiency of atmospheric escape. Similarly, planets orbiting close to active stars tend to have thinner atmospheres or none due to intense stellar wind and radiation stripping, while planets farther out or around quieter stars retain their atmospheres more easily. The coldest planet fits somewhere in this landscape, likely in a regime where atmospheric retention is favored by low temperature and hence low thermal escape, but challenged by the potential for condensation. The observational campaign to study this planet likely continues, with additional transits and eclipses being observed to improve signal-to-noise, to search for variability over time, and to probe different wavelength ranges. Combining Webb observations with data from other telescopes, such as Hubble and the ultraviolet and visible or ground-based telescopes with adaptive optics, provides a more complete spectral coverage and helps break degeneracies in atmospheric models. For example, ultraviolet observations can detect high-altitude hazes, ozone, or sulfur compounds that Webb cannot see. Radio observations might detect magnetic fields or ionospheric emissions. Synergistic observations maximize the scientific return. Public and scientific interest in this discovery stems from its novelty and its connection to the search for life. The phrase "atmosphere like Earth" resonates because Earth is the only known inhabited world, and finding planets with similar atmospheres raises the question of whether they, too, might harbor life. The coldness of this planet complicates that question. Life, as we know it, requires liquid water, which cannot exist at the surface of such a cold world. However, life might exist in subsurface environments if there is internal heating and liquid water beneath an ice shell, analogous to the hypothesized subsurface oceans of Europa or Enceladus, moons in our solar system. Detecting signs of subsurface life remotely is even more challenging than detecting surface or atmospheric life, because the biosignatures would be hidden below the ice. Nonetheless, the presence of oxygen and other gases might hint at processes occurring beneath the surface and venting into the atmosphere. The discovery also prompts consideration of human exploration or robotic missions, though the distances involved make such endeavors far beyond current capabilities. Exoplanets are light years away, and even the nearest, Proxima Centauri b, is over 4 light years distant, requiring travel times of tens of thousands of years with current propulsion technology. The coldest known planet with an Earth-like atmosphere is presumably farther. Thus, all knowledge of it must come from remote sensing, using telescopes to analyze light. Advances in telescope technology, such as future extremely large telescopes on the ground or next-generation space telescopes like the proposed Habitable Exoplanet Observatory, will enable more detailed studies, potentially imaging the planet directly, resolving surface features, or measuring rotation and day-night variations in real time. The physics of light and spectroscopy underpin all these observations. Light is electromagnetic radiation, consisting of oscillating electric and magnetic fields propagating through space at a fixed speed. Light can be described as a wave, characterized by wavelength and frequency, or as particles called photons, each carrying a quantum of energy. Molecules absorb and emit light at specific wavelengths corresponding to transitions between energy levels. These transitions can be electronic, involving electrons moving between orbitals, vibrational, involving atoms oscillating within a molecule, or rotational, involving the molecule spinning. Infrared spectroscopy primarily probes vibrational and rotational transitions. Each molecule has a unique set of allowed transitions, creating a barcode-like pattern of absorption and emission lines that serve as fingerprints for identification. When light from a star passes through a planet's atmosphere, molecules absorb photons at their characteristic wavelengths, reducing the intensity of light at those wavelengths. A spectrograph disperses the light, spreading it out by wavelength, and a detector records the intensity at each wavelength, producing a spectrum. By comparing the observed spectrum to laboratory measurements and theoretical calculations of molecular spectra, astronomers identify which molecules are present and estimate their abundances. The strength of an absorption line depends on the abundance of the molecule, the temperature and pressure of the gas, and the intrinsic strength of the transition, called the oscillator strength or Einstein coefficient. Hot gases have broader lines due to Doppler broadening from faster molecular motion, while cold gases have narrower lines. High-pressure gases have broader lines due to collisional broadening, where collisions between molecules interrupt transitions and blur the line profile. Low-pressure gases have narrower lines. The shape and width of spectral lines thus carry information about the physical state of the gas. In exoplanet atmospheres, pressure and temperature vary with altitude, and the observed spectrum is an integrated signal from all layers, weighted by the opacity and geometry. Sophisticated radiative transfer models simulate how light propagates through the atmosphere, accounting for absorption, emission, scattering, and a layered structure to predict the observed spectrum for a given atmospheric model. By comparing model predictions to observations, researchers infer the atmosphere properties. The significance of temperature in all this cannot be overstated. Temperature affects molecular speeds, spectral line widths, chemical reaction rates, phase equilibria, thermal emission intensity, and atmospheric structure. The coldest known planet's temperature, measured through its thermal emission and inferred from models fitting the spectral data, places it in a regime where familiar substances behave differently than on Earth. Water is solid ice. Carbon dioxide is near its frost point. Methane, if present, would be liquid or ice. Nitrogen and oxygen, however, remain gaseous, their boiling points far below the planet's temperature, allowing them to form an atmosphere. Understanding this environment requires applying thermodynamics and kinetic theory, the branches of physics that describe the behavior of matter and energy. Thermodynamics provides laws governing energy conservation, entropy, and equilibrium, while kinetic theory explains gas behavior in terms of molecular motion and collisions. Atmospheric circulation, the movement of air driven by temperature differences, rotation, and stellar heating, redistributes heat and material across the planet. On Earth, circulation patterns include the Hadley cells near the equator, Ferrel cells at mid-latitudes, and polar cells at high latitudes, driven by differential heating between equator and poles and influenced by the Coriolis effect from Earth's rotation. On a tidally locked exoplanet, circulation is dominated by day-night heat transport, with strong jets flowing from the hot day side to the cold night side and return flows at different altitudes or latitudes. The efficiency of this transport determines whether the night side remains warm enough to prevent atmospheric collapse. General circulation models, complex computer simulations solving the equations of fluid dynamics and thermodynamics on a spherical grid, predict wind speeds, temperature maps, and cloud patterns. For the coldest known planet, such models would explore scenarios with varying atmospheric mass, rotation rate, and heat capacity to identify which configurations match the observed temperature and spectral features. The question of whether life could exist on such a planet, or whether the atmosphere itself indicates life, remains open. Life, as understood from Earth, requires liquid water, a source of chemical energy, and a set of elements including carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The cold surface of this planet lacks liquid water, but subsurface reservoirs heated by tidal or radiogenic processes are conceivable. If microbial life exists below the ice and produces gases that vent into the atmosphere, those gases might be detectable. Oxygen production by photosynthesis or methane production by methanogenesis are two processes that could create detectable biosignatures. However, abiotic mimics exist. Oxygen can come from water photolysis and hydrogen escape. Methane can come from geologic processes. Distinguishing biotic from abiotic requires examining the full context. The abundances of multiple gases, their ratios, the presence of disequilibrium, the lack of obvious abiotic sources, and ideally, additional lines of evidence such as surface features or temporal variability consistent with biological activity. The community of scientists studying exoplanets brings together expertise from astronomy, planetary science, chemistry, physics, geology, and biology. Observers develop new instruments and techniques to detect and characterize distant planets. Theorists build models to interpret the data and predict phenomena. Laboratory scientists measure the properties of molecules and materials under the extreme conditions found on exoplanets, filling in gaps in the data needed for accurate models. Each discovery prompts new questions and drives further research. The coldest known planet with an Earth-like atmosphere exemplifies this collaborative, iterative process. The detection itself relied on decades of technological development, from the design and construction of the James Webb Space Telescope to the algorithms for data analysis. Interpreting the discovery requires understanding atmospheric physics, chemistry, stellar properties, orbital dynamics, and more. Communicating the discovery to the broader public involves explaining not just the result, but the methods, the significance, and the limitations of what is known. Limitations are always present. The spectrum has noise. The atmospheric models have assumptions. The planet may have clouds that obscure certain features. The abundances of gases are not determined to arbitrary precision, but come with error bars. Alternative models might fit the data nearly as well, leading to ambiguity. The temperature reported is an effective temperature, averaged over the observable hemisphere and possibly varying with time or location. The comparison to Earth is qualitative, not quantitative. The atmosphere is like Earth in that it contains nitrogen, oxygen, and carbon dioxide, but the exact ratios, pressures, and conditions may differ significantly. Saying the planet has an atmosphere like Earth is a heuristic, a way of conveying the discovery's novelty, not a claim of exact similarity. Future observations with higher precision and broader wavelength coverage will refine the understanding, potentially revealing additional molecules, measuring isotopic ratios, or detecting time-variable signals that indicate weather or volcanic activity. The timescale over which these observations unfold is also important. Exoplanet atmospheres do not change rapidly. A single transit or eclipse captures a snapshot, but planets orbit over days to years, and atmospheric circulation, chemistry, and clouds can vary on similar timescales. Observing the planet multiple times over months or years can reveal seasonal changes if the orbit is eccentric, rotational modulation if the planet is not tidally locked, or stochastic variability from storms or eruptions. Long-term monitoring builds a more complete picture. Some planets have already been observed dozens of times, allowing detailed studies of variability and long-term trends. The coldest planet's orbital period and observational cadence will determine how quickly such monitoring can accumulate. The host star spectrum must be well understood to accurately extract the planetary spectrum. Stars are not perfect blackbodies. They have absorption lines from elements in their atmospheres, emission lines from chromospheric or coronal activity, and variability from spots, flares, and oscillations. Stellar spectroscopy, the study of starlight, provides the baseline against which the planetary signal is measured. Any error in the stellar spectrum propagates into the planetary spectrum. Observations often include reference stars, other stars of similar type observed under the same conditions, to calibrate the instrumental response and correct for telluric or stellar contamination. The precision required to detect the tiny signals from cold exoplanet atmospheres pushes the limits of calibration accuracy. Instrumental calibration involves measuring the telescope's response as a function of wavelength, position on the detector, time, and other variables. This is done using standard stars with known spectra, internal calibration lamps, and repeated observations of the same target. Flat fields correct for pixel-to-pixel sensitivity variations. Dark frames correct for detector noise. Wavelength calibration maps detector pixels to wavelengths using emission lines from calibration sources. All these steps introduce uncertainties that must be carefully managed. The James Webb Space Telescope's instruments were extensively calibrated before launch and continue to be calibrated in flight, using onboard calibration sources and observations of well-characterized astronomical targets. The quality of the calibration directly impacts the reliability of the derived atmosphere properties. The coldest known planet's discovery also highlights the importance of archival data and reanalysis. Sometimes, planets are initially detected but not fully characterized, or early observations have insufficient signal-to-noise for detailed spectroscopy. As more data accumulate, or as analysis techniques improve, previously marginal detections become robust and new features emerge. Archival data from older telescopes, such as Hubble or Spitzer, can be reanalyzed in light of new knowledge from Webb, providing complementary wavelength coverage or longer time baselines. Data sharing and open access enable the broader scientific community to contribute to analysis, increasing the chances that subtle signals are noticed and properly interpreted. The narrative of discovery is rarely straightforward. Initial data might show hints of an atmosphere, but with large uncertainties. Follow-up observations improve the constraints. Different teams may analyze the same data and reach slightly different conclusions, prompting discussion and further investigation. Peer review and replication ensure that results are robust. The announcement that the James Webb Space Telescope has found the coldest known planet with an atmosphere like Earth represents the culmination of this process. Data have been collected, analyzed, modeled, peer-reviewed, and deemed sufficiently compelling to warrant public dissemination. Yet the discovery is not an end, but a beginning, opening new avenues for study and raising new questions. One question is how typical or atypical this planet is. Is it one of a kind? Or does every cool star have a cold planet with an Earth-like atmosphere waiting to be found? Answering this requires surveying many stars, detecting planets around them, and attempting to characterize their atmospheres. Surveys like TESS, the Transiting Exoplanet Survey Satellite, have identified thousands of candidate planets, and follow-up with Webb can determine which have atmospheres and what those atmospheres contain. Statistical analysis of the results will reveal trends and outliers. If cold, Earth-like atmospheres are common, this suggests that the formation and retention of such atmospheres is a natural outcome under certain conditions, and understanding those conditions will be key. If they are rare, the specific circumstances that allowed this planet to develop its atmosphere become all the more interesting. The possibility of atmospheric biosignatures on cold planets shifts the focus of the search for life beyond the traditional habitable zone. The habitable zone, defined as the range of orbital distances where liquid water can exist on a planet's surface, is a useful but simplistic concept. It assumes an Earth-like atmosphere and neglects factors like greenhouse gases, albedo, internal heating, and tidal forces. Planets outside the habitable zone might still be habitable in subsurface oceans or might have atmospheric chemistry influenced by life without hosting surface life. Broadening the search to include cold planets increases the number of targets and the diversity of environments considered. It also complicates the interpretation of biosignatures, because cold planets may have abiotic processes that mimic biological ones or biological processes that produce unexpected signals. The study of this planet also informs the design of future missions. Knowing that cold planets with Earth-like atmospheres exist, and that their atmospheres can be characterized with existing technology, encourages the development of even more sensitive instruments tailored to this science. Proposed missions like the Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, and the Habitable Exoplanet Observatory, or HABEX, aim to directly image rocky planets in the habitable zones of nearby stars, blocking the star's light with a coronagraph or star shade and capturing the faint reflected light from the planet. Such missions could observe planets over full orbits, measuring seasonal variations, mapping surface features, and detecting oceans, continents, and clouds. Extending these capabilities to colder planets would require larger telescopes or longer observation times, but the scientific payoff could be enormous. The interplay between theory and observation drives progress. Theoretical models predict what kinds of planets should exist, how their atmospheres should behave, and what signals they should produce. Observations test these predictions, sometimes confirming them, sometimes revealing surprises that require new theories. The coldest known planet with an Earth-like atmosphere may confirm some theoretical expectations, such as the persistence of nitrogen atmospheres at low temperatures given appropriate pressure and gravity. Or it may surprise, such as if the oxygen abundance is higher than any abiotic model predicts, hinting at unknown chemistry or biology. Either outcome advances understanding. The role of chance and observational strategy also matters. Discovering this planet required that it transits its star as seen from Earth, a geometric alignment with only a few % probability for any given planet. Thousands of stars must be monitored to find transiting planets, and among those, only a subset will have planets with atmospheres amenable to characterization. Targeting the right stars, those with favorable properties like brightness, quietness, and appropriate distance, increases the chances of success. Surveys and follow-up programs are designed with these considerations in mind, balancing the breadth of sky coverage with the depth of observation needed for detailed studies. The coldest planet's atmosphere likely exhibits unique chemical processes due to the low temperature. Reaction rates slow exponentially with decreasing temperature, described by the Arrhenius equation, meaning that reactions that proceed rapidly on warm planets may be negligible on cold planets. Conversely, cold temperatures favor the formation of complex molecules through barrierless reactions or low activation energy pathways. In the outer solar system, on moons like Titan and Triton, cold temperatures enable rich organic chemistry, producing tholins, nitriles, and other compounds. On the coldest exoplanet, if organic precursors are present, similar chemistry might occur, though the composition and stellar radiation environment would differ from Titan. Detecting organic molecules in the atmosphere would be significant, as organics are the building blocks of life, and their presence indicates chemical complexity. The energy budget of the planet includes not only stellar irradiation, but also potential internal heat. Planets generate internal heat through radioactive decay of isotopes like uranium, thorium, and potassium in their interiors. Young planets also retain heat from their formation, when gravitational potential energy was converted to thermal energy during accretion. Gas giants and ice giants can have significant internal heat sources, which contribute to their total luminosity and affect their atmospheric temperature. Rocky planets generally have weaker internal heat sources, but tidal heating, caused by gravitational interactions with a companion planet or moon, can be substantial. If the coldest planet is part of a multi-planet system or has a large moon, tidal forces could flex the interior, generating heat and possibly driving volcanic or cryovolcanic activity, which would inject gases into the atmosphere and help sustain it. The detection of multiple molecules in the atmosphere allows for chemical network modeling. Chemical networks are sets of reactions linking different species, each with a rate constant. By solving the system of differential equations governing the concentrations of each species over time, modelers predict the steady-state composition of the atmosphere under given conditions. These models can include hundreds of species and thousands of reactions, accounting for photochemistry, thermochemistry, and transport. Comparing the model output to observations helps identify which reactions are most important and whether the observed composition can be explained by known chemistry or requires additional processes. The history of planetary science includes many examples where unexpected atmospheric compositions prompted new understanding. Venus's thick carbon dioxide atmosphere and runaway greenhouse effect was not predicted before measurements. Mars's thin atmosphere and loss of water surprised early observers. Jupiter's atmospheric dynamics, including the Great Red Spot and zonal jets, continue to challenge models. Titan's nitrogen-methane atmosphere was unexpected for a moon. Each discovery refined theories and expanded the known diversity of planetary atmospheres. The coldest exoplanet with an Earth-like atmosphere adds another data point, expanding the diversity into new temperature regimes and compositional space. The philosophical implications of finding Earth-like atmospheres around other stars touch on humanity's place in the universe. For millennia, Earth was thought to be unique, the center of creation. The Copernican revolution displaced Earth from the center of the solar system. Later discoveries showed the Sun is one star among billions in a galaxy, and the galaxy one among billions in the observable universe. The detection of exoplanets confirmed that planets are common. Finding planets with atmospheres resembling Earth's, even if those planets are not habitable, further diminishes Earth's uniqueness. It suggests that the processes that shaped Earth's atmosphere are not rare or special, but are instead natural outcomes of planetary evolution under certain conditions. This raises the likelihood that life-bearing planets exist elsewhere, because if Earth-like conditions can arise in diverse environments, the opportunities for life are correspondingly diverse. Yet each planet is also unique in its details. The coldest planet may have an Earth-like atmosphere and gross composition, but its specific mixture, pressure, temperature profile, cloud structure, surface conditions, and history are its own. No two planets are identical. Understanding both the commonalities and the differences is the goal of comparative planetology. The commonalities reveal universal physical laws and formation processes. The differences reveal the contingent factors, the specific circumstances that make each planet distinct. The communication of science to the public involves balancing accuracy with accessibility. Statements like the coldest known planet with an atmosphere like Earth are designed to convey the essence of the discovery in a compact, memorable phrase. They sacrifice precision for clarity. The detailed reality, involving effective temperatures, equilibrium calculations, spectral line fitting, vapor pressure curves, and atmospheric modeling, is too complex for a headline, but is essential for scientific understanding. Popular articles, documentaries, and educational materials serve as bridges, translating technical findings into language that engages broad audiences without misleading them. The challenge is to maintain the wonder and significance of the discovery while accurately representing the uncertainties and the methods. The trajectory of future research on this planet will likely include multi-band photometry to measure the planet's brightness at different wavelengths over time, revealing rotational modulation or phase curves that show how brightness changes as different hemispheres face the telescope. This can constrain the day-night temperature difference and the efficiency of heat transport. It will include higher resolution spectroscopy to resolve finer features and detect additional molecules. It will include observations at different orbital phases to probe different parts of the atmosphere, such as the terminator region during transit versus the day side during secondary eclipse. It will include comparative studies with other cold planets, once more discovered, to identify trends and test hypotheses. The discovery also exemplifies the iterative nature of science. Early models of exoplanet atmospheres were simple, assuming isothermal, cloud-free, well-mixed conditions. As observations improved, models became more complex, adding temperature gradients, clouds, chemical disequilibrium, and three-dimensional dynamics. Each new observation tests the models, and when discrepancies arise, models are refined. The coldest planet's atmosphere may fit existing models well, validating them, or may show features that require new physics or chemistry to explain. Either outcome is valuable. Science progresses through both confirmation and surprise. The technical achievement of the James Webb Space Telescope itself deserves recognition. Designing and building an infrared space telescope operating at cryogenic temperatures, with a segmented deployable mirror, complex sun shield, and precision instruments required decades of engineering, testing, and problem-solving. The successful deployment and commissioning of Webb was a triumph of collaboration, involving thousands of engineers, scientists, and technicians from multiple countries. The telescope's performance has exceeded expectations in many areas, enabling discoveries that were hoped for but not guaranteed. The detection of the coldest planet with an Earth-like atmosphere is one of many breakthroughs Webb is making, reshaping our view of the universe. Atmospheric escape processes deserve deeper consideration. Escape is not a single phenomenon, but a collection of processes acting differently on different gases. Thermal escape affects light gases preferentially, with hydrogen escaping fastest, followed by helium. Heavier gases like nitrogen and oxygen escape much more slowly. Non-thermal escape includes processes like ion pickup, where ionized atoms are swept away by stellar wind, and sputtering, where energetic particles knock atoms out of the atmosphere. Photochemical escape involves chemical reactions at high altitudes, producing molecules or atoms with enough energy to escape. Hydrodynamic escape occurs when a large flux of escaping light gas, such as hydrogen, drags heavier gases along. On the coldest planet, thermal escape of nitrogen and oxygen is negligible because the low temperature means low average molecular speeds, well below escape velocity. Non-thermal escape depends on stellar wind strength, ultraviolet flux, and magnetic shielding, which are not directly measured but can be inferred from the star's type and activity. The persistence of the atmosphere suggests escape rates are low or balanced by outgassing or other replenishment. The magnetic field of the planet, if present, provides a shield against stellar wind and charged particles. Earth's magnetic field deflects the solar wind, protecting the atmosphere from being stripped away. Mars lacks a global magnetic field, and its thin atmosphere is partially a result of billions of years of solar wind erosion. The coldest planet's magnetic field strength is not measurable remotely with current techniques, but theoretical considerations suggest that if the planet has a molten, conducting core and rotates sufficiently fast, it could generate a dynamo magnetic field. A thick ice shell might insulate the core, but tidal heating could keep the interior warm enough for a dynamo. Alternatively, the planet might lack a magnetic field, and the low stellar wind at its orbital distance might be insufficient to strip the atmosphere significantly. The implications for climate science are also worth exploring. Climate is the long-term average of weather, shaped by energy input, atmospheric composition, surface properties, and dynamics. Earth's climate has varied dramatically over geologic time, from snowball Earth episodes where ice covered the entire surface to hothouse climates with no polar ice. These variations arose from changes in solar luminosity, orbital parameters, volcanic activity, and biological feedbacks. Understanding how planetary climates respond to changes in forcing is crucial for predicting Earth's future climate and for interpreting exoplanet observations. The coldest planet provides a test case for climate models in an extreme regime. How does an atmosphere behave when the energy input is so low? What feedbacks arise? Is the climate stable, or are there tipping points where small changes cause large shifts, such as atmospheric collapse? Radiative transfer, the propagation of light through the atmosphere, is the key process linking the star's energy to the planet's climate. Incoming stellar radiation at visible wavelengths passes through the atmosphere, with some fraction absorbed by gases, aerosols, and the surface, and some reflected or scattered back to space. The absorbed energy heats the surface and lower atmosphere, which then emit infrared radiation. Greenhouse gases absorb some of this infrared radiation and re-emit it in all directions, including back toward the surface, trapping heat. The balance between incoming visible light and outgoing infrared radiation determines the planet's temperature. On a cold planet with few greenhouse gases, most of the infrared radiation escapes directly to space, and the surface temperature is close to the equilibrium temperature. This is why the coldest planet, with a nitrogen-oxygen atmosphere, is so cold. Nitrogen and oxygen do not trap heat. The surface of the coldest planet, if solid, could be composed of ice, rock, or mixture. Water ice is a likely major component, given the low temperature. Carbon dioxide ice, methane ice, nitrogen ice, and ammonia ice could also be present depending on the planet's formation history and volatile budget. The surface might be geologically active, with tectonic features, cryovolcanoes, or impact craters, or it might be inactive and ancient, preserving a record of early bombardment. Remote sensing cannot resolve surface features at interstellar distances, but future direct imaging missions might detect surface compositions through spectroscopy of reflected light, distinguishing ice types by their characteristic reflectance spectra. The orbital dynamics influence the planet's climate and atmospheric stability. If the orbit is circular and the rotation is synchronous, the climate is relatively steady, with constant stellar irradiation on the day side and perpetual darkness on the night side. If the orbit is eccentric, the planet's distance from the star varies, causing seasonal temperature changes. If the rotation is not synchronous, the planet experiences day-night cycles, and the atmosphere must respond to periodic heating and cooling. The length of the day, the rotation period, affects atmospheric circulation patterns. Slow rotation leads to weak Coriolis forces and simple circulation, while fast rotation leads to strong Coriolis effects and complex jet streams. Earth's rotation period is 24 hours, leading to mid-latitude jet streams and cyclonic weather systems. A tidally locked planet with an infinitely long day has no Coriolis effect from day-night rotation, but still has Coriolis effects from any residual rotation or libration, the slight wobble due to orbital eccentricity or obliquity. The possibility of moons orbiting the coldest planet introduces additional complexity. Moons exert tidal forces on the planet, generating heat if the planet's orbit is eccentric or if the moon's orbit is inclined. The moon could also have its own atmosphere, and interactions between the planet and moon, such as exchange of material through impacts or volcanism, could affect both. Detecting exomoons is extremely challenging, requiring precise measurements of transit timing variations or subtle distortions in the light curve. So far, no exomoons have been confirmed, though several candidates have been proposed. If the coldest planet has a large moon, this would add another dimension to its characterization and evolutionary history. The long-term fate of the planet's atmosphere depends on many factors. If the star evolves, increasing in luminosity as it ages, the planet will warm, and the atmosphere may thaw, transitioning from a cold regime to a temperate or even hot regime over billions of years. If the planet is captured by another star, or if the star's orbit within the galaxy changes, the stellar environment could shift. Galactic cosmic rays and nearby supernovae or gamma-ray bursts could affect the atmosphere through ionization and chemical reactions. Over truly cosmological timescales, the expansion of the universe and the eventual fate of the star, whether it becomes a white dwarf, neutron star, or black hole, will end the planet's current state. These are speculative considerations, far beyond current observational reach, but they highlight the dynamic, evolving nature of planetary systems. The nitrogen cycle on this planet would differ greatly from Earth's. On Earth, nitrogen cycles through the atmosphere, biosphere, hydrosphere, and lithosphere, with processes like nitrogen fixation by bacteria, denitrification, lightning-induced reactions, and volcanic emissions driving exchanges between reservoirs. On a lifeless, cold planet, the nitrogen cycle would be abiotic, perhaps involving photochemical reactions in the upper atmosphere, condensation and sublimation on the surface, and slow geological sequestration in minerals or ice clathrates. If life exists, biological nitrogen fixation or other metabolic processes could alter the cycle, potentially creating detectable signals such as unusual isotopic ratios or the presence of nitrogen-bearing organic compounds. The oxygen cycle, similarly, would be radically different without life. On Earth, photosynthesis produces nearly all atmospheric oxygen, and respiration, decay, and combustion consume it, maintaining a rough balance modulated by the burial of organic carbon. On a cold exoplanet, oxygen sources might be photolysis of water or carbon dioxide, with sinks including oxidation of surface minerals, reaction with volcanic gases like hydrogen sulfide or sulfur dioxide, and escape to space of lighter isotopes. The balance determines the steady-state oxygen abundance. If the detected oxygen is maintained abiotically, this implies a specific set of conditions: sufficient ultraviolet radiation for photolysis, inefficient sinks, and stability over time. If the oxygen is biological, it implies active ecosystems producing oxygen faster than sinks remove it, similar to Earth after the Great Oxidation event 2.4 billion years ago. The water cycle on this cold planet is constrained by temperature. Liquid water cannot exist on the surface, so the cycle is limited to sublimation of surface ice, transport of water vapor through the atmosphere, and redeposition as frost or snow. This is analogous to the water cycle on Mars, where the thin atmosphere and cold temperatures restrict water to the solid and vapor phases, with occasional transient brines in localized warm spots. On the coldest planet, atmospheric water vapor concentration would be extremely low due to the low saturation vapor pressure, and clouds, if they form, would be composed of ice crystals. These clouds might be visible in reflected light as high albedo features and in transmission spectra as scattering or absorption features. The carbon cycle involves exchanges of carbon dioxide between the atmosphere, surface, and interior. On Earth, the long-term carbon cycle regulates climate through the weathering of silicate rocks, which consumes carbon dioxide, and volcanic outgassing, which releases it. This feedback stabilizes Earth's temperature over geologic time. On a cold planet, silicate weathering is negligible because liquid water is absent and reaction rates are low. Carbon dioxide might accumulate in the atmosphere from outgassing until it condenses and deposits on the surface as dry ice. Alternatively, carbon dioxide could be sequestered in carbonate minerals or ice clathrates, removing it from the atmosphere. The observed carbon dioxide abundance constrains these processes, indicating either ongoing outgassing, slow sinks, or an atmosphere in transient imbalance. The planet's geological history would shape its current state. If it formed with a thick primordial atmosphere of hydrogen and helium, subsequent loss would have stripped these light gases, possibly along with some heavier gases dragged along hydrodynamically. If large impacts occurred early, They could have excavated portions of the atmosphere or deliver volatiles from impactors. If differentiation occurred, separating the planet into a metal core, silicate mantle, and crust, the timing and completeness of differentiation would affect volcanic activity and outgassing. If plate tectonics or other forms of crustal recycling operate, they would modulate the exchange of volatiles between surface and interior. On Earth, plate tectonics plays a crucial role in the carbon cycle, subducting carbonates into the mantle and recycling carbon through volcanism. On a cold, possibly geologically inactive planet, such processes might be absent, leading to a static atmosphere that reflects initial conditions rather than ongoing activity. The search for analogs in the solar system provides context. No solar system planet matches the coldest exoplanet precisely, but Titan, Pluto, Triton, and other icy moons and dwarf planets offer comparisons. Titan has a thick nitrogen atmosphere with methane, maintained by photochemistry and possibly cryovolcanism, and a surface temperature of 94 Kelvin. Pluto has a thin nitrogen atmosphere that may freeze out when Pluto moves farther from the Sun in its eccentric orbit. Triton has a thin nitrogen atmosphere with trace methane and a surface temperature of 38 Kelvin, possibly sustained by solar heating of dark surface patches and nitrogen geysers. Studying these bodies with spacecraft missions provides detailed data unattainable for exoplanets, such as in-situ measurements, surface imaging, and direct sampling. Lessons learned from solar system exploration inform interpretations of exoplanet data. The role of stellar ultraviolet and X-ray radiation in shaping atmospheres is multifaceted. Ultraviolet photons ionize and dissociate molecules, driving photochemistry and potentially eroding atmospheres through photochemical escape. X-rays heat the upper atmosphere, causing it to expand and become more vulnerable to escape. However, ultraviolet radiation also drives processes that could replenish atmospheres, such as photolysis of water releasing oxygen. The balance depends on the intensity and spectrum of the radiation, the atmospheric composition, and the planet's gravity. Observing the host star's ultraviolet and X-ray emission, either with dedicated space telescopes or by inferring from proxies like optical emission lines, helps model the planet's atmospheric evolution. The concept of planetary habitability has evolved over time. Originally defined narrowly as the presence of liquid water on the surface, it has broadened to include subsurface habitability, habitable zones in atmospheres of gas giants, and even exotic possibilities like ammonia-based life in cold environments or silicon-based life in high-temperature settings. The coldest planet with an Earth-like atmosphere expands the conception of where to search for life-related processes. Even if the surface is inhospitable, subsurface environments heated by tidal or radiogenic processes could harbor life, and atmospheric gases could provide clues. The definition of habitability must accommodate the diversity of environments and the adaptability of life, at least as far as we can imagine based on Earth's extremophiles and theoretical biochemistry. The ethical and philosophical dimensions of discovering life beyond Earth, or even potential evidence for life, are profound. It would answer one of humanity's oldest questions, confirm that life is not unique to Earth, and raise new questions about the nature and distribution of life in the universe. It would affect theology, philosophy, ethics, and culture. The search for life is thus not just a scientific endeavor, but a human one, driven by curiosity and the desire to understand our place in the cosmos. The coldest planet, even if not inhabited, contributes to this search by expanding the catalog of environments and testing our understanding of atmospheric chemistry and planetary habitability. The detection techniques used for the coldest planet exemplify the power of precision measurement. The difference between the star's brightness with and without the planet's thermal emission is minuscule, parts per 10,000 or smaller. Extracting this signal requires subtracting the star's variability, correcting for instrumental drifts, and integrating over long times to build signal-to-noise. Statistical methods, such as maximum likelihood estimation and Bayesian inference, provide frameworks for estimating parameters and their uncertainties given noisy data. Bayesian methods, in particular, allow incorporation of prior knowledge, such as the expected range of temperatures or compositions, and yield posterior probability distributions for parameters, quantifying confidence in the results. The language used to describe discoveries must be precise yet communicative. Terms like Earth-like are inherently vague, encompassing a range of meanings from similar size and mass to similar composition or similar temperature. In the context of this discovery, Earth-like refers to atmospheric composition, specifically the presence of nitrogen, oxygen, and carbon dioxide, not to temperature or habitability. Clarifying these distinctions prevents misunderstandings. Similarly, coldest known planet is accurate as of the discovery announcement, but subject to revision as new discoveries are made. The scientific literature continually updates records as better data emerge or new objects are found. The funding and policy environment supporting exoplanet research reflects societal priorities. Governments and international agencies allocate resources to build telescopes, support observing programs, and fund researchers. These investments reflect a collective judgment that understanding the universe, discovering new worlds, and searching for life are valuable endeavors. Public engagement and education amplify the impact of discoveries, inspiring the next generation of scientists and fostering scientific literacy. The coldest planet's discovery, like others before it, contributes to this broader cultural and intellectual project. The challenges of detecting biosignatures on cold planets are substantial but not insurmountable. Biosignatures are signs of life, such as gases like oxygen or methane in disequilibrium, surface pigments from photosynthetic organisms, or temporal variability inconsistent with abiotic processes. On a cold planet, biosignatures might be subtle. Oxygen at low abundance might be explained by photolysis. Methane might be geologic. Pigments would not be detectable remotely without direct imaging and spectroscopy of the surface. Temporal variability could be due to seasonal cycles or volcanic events. Multiple independent lines of evidence would strengthen the case for life. For example, detecting oxygen, methane, and water vapor together, with abundances inconsistent with known abiotic chemistry, would be suggestive. Detecting ozone, a secondary product of oxygen photochemistry, would support the presence of oxygen. Detecting complex organic molecules would indicate rich chemistry. None alone is definitive, but together they build a circumstantial case. The discovery process for exoplanets often involves serendipity as well as targeted searches. Sometimes planets are found in data originally collected for other purposes. Sometimes anomalies prompt deeper investigation. The coldest planet may have been identified in a survey targeting many stars, or it may have been a focused follow-up of a known transiting planet to characterize its atmosphere. The details of the discovery path, including how the target was selected, how the data were collected, and how the atmosphere was detected, are documented in the scientific literature and provide valuable lessons for future searches. The interdisciplinary nature of exoplanet science brings together techniques from multiple fields: astronomy for observing stars and detecting planets, physics for understanding radiation and energy, chemistry for modeling molecular interactions, geology for interpreting surface and interior processes, atmospheric science for modeling climate and circulation, and biology for assessing habitability and biosignatures. This synthesis of disciplines enriches the science, allowing comprehensive understanding that no single field could achieve alone. The coldest planet's characterization draws on all these areas, integrating knowledge to construct a coherent picture. As the field matures, standardization of terminology, methods, and data formats facilitates collaboration and reproducibility. Open data archives allow researchers worldwide to access observations, fostering independent analyses and new discoveries. Community-developed software tools for data reduction, spectral modeling, and statistical analysis lower barriers to entry and increase efficiency. Workshops and conferences bring researchers together to share results, debate interpretations, and plan coordinated observations. These collaborative structures accelerate progress and enhance the robustness of conclusions. The coldest planet stands as a testament to human ingenuity and curiosity, a world revealed not through direct exploration, but through the careful analysis of photons that traveled across light years of space. Its atmosphere, cold and thin, yet bearing the chemical signatures of gases familiar from Earth, challenges simple narratives about planetary climates and atmospheres. It exists at the margins of what current technology could detect and characterize, pushing observers and theorists to refine their methods and expand their models. It offers no immediate practical benefit, yet it enriches understanding of the cosmos and humanity's place within it. The atmosphere clings to the planet despite the cold, held by gravity against the pull of stellar wind and the tendency of molecules to condense and freeze. The gases circulate, driven by faint sunlight and internal heat, if any exists, redistributing warmth and cold, perhaps creating weather patterns too subtle to detect, but real nonetheless. Water vapor, carbon dioxide, nitrogen, oxygen, each molecule a traveler in the thin air, colliding with others, absorbing and emitting photons, rising and falling through pressure gradients, participating in slow chemistry that shapes the composition over eons. The surface below, if visible from above, might be an icy expanse, cracked and cratered, bright with frost or darkened by organic tholins, silent and still in the dim light of a distant star. The data captured by the James Webb Space Telescope encoded all this information in the form of a spectrum, a graph of intensity versus wavelength. To the uninitiated, the spectrum is a jagged line, peaks and valleys marching across the plot. To the trained eye, each peak is a molecule announcing its presence, each valley an absence where absorption occurred. The spectrum is a conversation between the planet and the observer, mediated by light. The planet speaks through its thermal glow, through the starlight filtered by its air. The telescope listens, collecting photons one by one, channeling them through mirrors and gratings, recording their wavelengths and intensities. The scientists interpret, comparing the data to libraries of molecular spectra, adjusting models until theory and observation align. Uncertainty threads through every step. The spectrum has noise, random fluctuations obscuring the true signal. The models have assumptions, simplifications necessary to make calculations tractable. The atmosphere itself may be more complex than models can capture, with spatial variations, time dependence, and processes not yet included in simulations. The reported atmospheric composition is a best estimate, not a definitive answer. Error bars on each parameter span a range of values consistent with the data. Alternative models might fit nearly as well, differing in details but agreeing on broad features. This uncertainty is not a flaw, but an inherent part of science at the frontier, where knowledge is hard-won and provisional, subject to revision as better data and refined theories emerge. The cold persists, unrelenting, governed by the simple physics of energy balance. The planet absorbs a trickle of energy from its star, spread over its dayside, perhaps shared with the night through atmospheric winds. It radiates that energy away as infrared light, glowing faintly in wavelengths invisible to the human eye, but captured by infrared detectors in space. The temperature settles at the point where absorbed energy equals emitted energy, and that point is far below the freezing point of water, far below the comfort of Earth, approaching the threshold where familiar gases begin their phase transitions toward solid forms. Yet the atmosphere does not collapse. It persists, defying intuition, maintained by the delicate balance of vapor pressure and atmospheric pressure, by the supply and loss rates of gases, by the gravity of the planet and the warmth, however faint, from the star. The nitrogen and oxygen remain aloft, molecules bouncing against one another, resisting the cold's pull toward the surface. The water vapor and carbon dioxide trace out their cycles, subliming and condensing, reacting and diffusing, present in concentrations small but measurable. The atmosphere is thin, perhaps, compared to Earth's, exerting a surface pressure of only tens or hundreds of pascals rather than 100,000, but it is there, a shell of gas wrapped around a distant world, and its existence is no less remarkable for its fragility. The discovery prompts reflection on the diversity of worlds. Each planet is an experiment in physics and chemistry, a natural laboratory where conditions differ and outcomes vary. Some planets bake under intense stellar heat, their atmospheres stripped or puffed up into vast envelopes. Others freeze in the outer dark, their volatiles locked in ice. Some spin rapidly, creating strong weather systems. Others are tidally locked, with permanent day and night. Some have magnetic fields, others do not. Some are geologically active, others are dead. The range of possibilities is vast, and each discovered planet samples a point in this multidimensional space. The coldest known planet with an Earth-like atmosphere occupies a unique point, defined by its low temperature and familiar gas mix. A point that was previously empty in the catalog and is now filled, shrinking the unknown and expanding the known. The act of observation itself is an achievement. Light from the host star, emitted by nuclear fusion in the star's core, traveled outward through the star's layers, escaped into space, and journeyed across the star system. Some of that light illuminated the planet, warming it infinitesimally, and some passed through or reflected off the planet's atmosphere, acquiring the spectral imprint of atmospheric gases. The light then traveled across the interstellar void, crossing distances measured in light years, undimmed by scattering in the near vacuum of space, until it entered the solar system, passed Earth's orbit, and fell upon the mirrors of the James Webb Space Telescope. There, photons were collected, focused, dispersed, and detected, their energies and arrival times recorded. The entire chain, from stellar fusion to telescope pixel, is a physical process describable by electromagnetism, quantum mechanics, and relativity. Yet the complexity and improbability of capturing and interpreting those photons is staggering. The coldest planet has no name beyond its designation in astronomical catalogs, a string of letters and numbers indicating the survey and order of discovery. It may receive a popular name in time, chosen to reflect some aspect of its nature or discovery, but for now it remains anonymous, known by its properties and its place in the data. The absence of a personal name does not diminish its significance. The planet exists regardless of human knowledge, orbiting its star, its atmosphere stirring in response to faint stellar heat, its surface marked by whatever geology or ice tectonics shape it. The discovery brings the planet into human awareness, but the planet itself is indifferent, continuing its orbit as it has for billions of years and will for billions more. The implications of the discovery ripple outward. Other researchers will propose follow-up observations, seeking to confirm the findings, refine the atmospheric parameters, or search for additional features. Theorists will incorporate the data into models, testing whether existing theories accommodate this planet or require modification. Educators will use the discovery as a teaching moment, explaining spectroscopy, thermal physics, and the search for life. The public will wonder at the existence of such a world, imagining its alien skies and frozen landscapes, pondering whether life could arise in such cold. All these responses stem from the same source, a set of data painstakingly acquired and carefully analyzed, revealing something new about the universe. The narrative of this planet, as told through its atmosphere, is incomplete. Much remains unknown. The exact temperature profile with altitude, the wind speeds, the cloud coverage, the surface composition, the presence of moons or ring systems, the planet's internal structure, its magnetic field strength, its formation history. All these are hidden or only partially constrained. Future observations may fill in some gaps, but others may remain forever beyond reach, given the planet's distance and faintness. Science progresses by reducing uncertainty, but perfect knowledge is unattainable. What is achieved is a useful, tested, empirically grounded understanding that allows prediction and explanation within defined limits. The cold planet orbits in darkness relative to human eyes, too faint and distant to be seen, except as a statistical fluctuation in starlight. It will never be visited by spacecraft in the foreseeable future. It will never host a colony or be touched by human hands. Its significance lies entirely in what it reveals about the universe and the processes that govern planetary systems. It expands the empirical basis for planetary science, providing data that inform understanding not just of that one world, but of all worlds, including Earth. Comparative planetology seeks to understand what is universal and what is contingent, what aspects of planets arise inevitably from physical law, and what depend on specific historical events. The coldest planet, with its unexpected atmospheric composition maintained in frigid conditions, contributes a crucial data point to this endeavor. The atmosphere is a fragile thing, a temporary accumulation of gas held against the void by gravity and circumstance. Over deep time, atmospheres evolve, thicken or thin, change composition, sometimes vanishing entirely. Earth's atmosphere has undergone dramatic transformations, from a reducing atmosphere of hydrogen and methane to an oxidizing one with free oxygen. Venus's atmosphere thickened into a crushing, scorching blanket of carbon dioxide. Mars's atmosphere thinned to a wisp. The coldest planet's atmosphere, observed in a single moment of cosmic time, is a snapshot of an ongoing process, and its future is uncertain. Will stellar evolution warm the planet, thickening the atmosphere and perhaps allowing liquid water? Will volcanic activity cease, and the atmosphere slowly condense away? Will impacts strip portions of it, or will it remain largely unchanged, a stable, cold shell for billions of years? Only time, and further observation if possible, will reveal the answer. The discovery encapsulates the modern scientific enterprise: global collaboration, advanced technology, rigorous methodology, peer review, open data, and public communication. It is science functioning as intended, incrementally building knowledge through observation and reasoning. It is also a reminder of the limits of knowledge and the vastness of what remains to be explored. Each answer raises new questions. Why does this planet have the atmosphere it does? Are there others like it? What does it tell us about planetary formation? Could life exist there, hidden beneath the ice? These questions drive future research, ensuring that the discovery is not an endpoint, but a waypoint on a longer journey. The physics and chemistry that govern the coldest planet's atmosphere are the same physics and chemistry that govern Earth's atmosphere, that govern the Sun, that govern all matter in the universe. The laws are universal, tested in countless contexts, and they apply equally to a laboratory on Earth, to the atmosphere of a distant exoplanet, and to the interior of a neutron star. This universality allows prediction and interpretation across astronomical distances. By observing light from a planet light years away and applying known physical principles, scientists can infer temperature, composition, and structure with remarkable accuracy. This is the power of physics. It transcends locality, providing tools to understand phenomena far beyond direct reach. The story of the coldest known planet with an atmosphere like Earth is a story of photons and molecules, of gravity and temperature, of observation and inference. It is a story written in spectra and data tables, in models and equations, in the collaborative work of researchers across continents and disciplines. It is a story without a clear ending, because the planet continues its existence and future discoveries will add chapters. It is a story that expands human knowledge and challenges assumptions, revealing a universe more diverse and wondrous than simple imagination could conjure. It is a story grounded in evidence, built on the foundation of centuries of scientific progress, and pointing toward questions that will occupy scientists for generations to come. The planet orbits, the atmosphere persists, the data accumulate, and understanding deepens, incrementally approaching truth while acknowledging the vast unknown that remains. The cosmos holds countless such worlds, each with its own story, and the coldest planet is but one among them, exceptional in its properties, ordinary in its existence, a reminder that the universe is rich with phenomena awaiting discovery and comprehension.